For our next talk, we have Professor Josiney Souza. He's professor at UEM, Universidade de Maringá, and he got his PhD at Unicamp under Professor San Martin's advisor. He studies, he works on topological dynamics, right, and dynamical systems. And today he's going to talk about on periodic points of invariant control systems.
Thank you, Jordan. Thank you, organizer, for the invitation. It's my pleasure to present you something about my research. And it's my pleasure to see you again. And my talk is about a simple relation between some dynamical concepts and Lie groups. I'd like to show you a relation between periodic point and recurrent point, a relation between uniformly recurrent point and Lie groups. So all these concepts are from dynamical systems and were recently on the context of control system on the group. Then I'd like to show you a simple connection among all these concepts. So in my talk, the letter G is a Lie group, and consider its algebra of the right invariant vector fields. So consider an invariant control system on G of this form. Piecewise control functions and compact and complex control range. Of course, with right invariant vector fields. Okay, these conditions imply the continuity of the phase map. So it should be remembered that the solutions of an invariant control system satisfy the invariance property, like here. So this invariant properties are important to the main result. Should we remember that the positive semi-orbit of the identity of the Lie group is a semi-group of G and coincides with the system semi-group of the system. So because of the invariance property, if the positive semi-orbit of the identity is compact or closed, all positive semi-orbit are respectively closed or compact. Okay, so in order to define the recursive concept, we need to define some sets. For t bigger than 0, a positive number, we define the t positive semi-orbit as the set here. That's the trajectories through X from time t, right? And we also define the positive limit set of X, that is the intersection of all t positive semi-orbit of X. Then we can define the recursive concept. So a point X in G is periodic if X belongs to its zero positive semi-orbit, right? And X is recurrent if X belongs to its positive limit set. This is the Poincaré recurrence, or the Poisson stability from dynamical systems. So finally, X is uniformly recurrent if the closure of this positive semi-orbit is a positive minimal set, right? So all these notions are related to the recursive concept. So they are related to the property that returning trajectories at positive time. So in the case of an invariant control system only group, in certain sense, this is related to existence of inverse element in the system same group. So we associate this concept to Lie groups, to Lie subgroup of G. This is the main result. So some remarks. Note that a point X is periodic if and only X is X belongs to all T positive semi-orbit of X. So a periodic point is recurrent. So this happens in the context of dynamical system. A subset M in G is a positive minimal set if and only M coincides with the closure of all T positive semi-orbit of X for all X in M. And which is the same thing, M coincides with the positive limit set of X for all X in M. So a uniformly recurrent point is also recurrent, right? Then the recurrence is the more general concept among these three concepts, these three recursive concepts, right? So because of the invariance property of the solutions, we can see that all state points are periodic if the identity is periodic. All points are uniformly recurrent if the identity is uniformly recurrent. And all points are recurring if and only if the identity is recurrent. So this is in fact a nice property of the, the invariant control systems, and because we can only study the identity if if you know what happened with the identity, we know what happened with all points in G. So let us see a simple example just to motivate the main result. Let G, the linear group of all 2 plus 2 real matrices, and consider. Jordan, let me know, please let me know if the connection sleeps, right?
Yeah, your connection is kind of struggling a little bit. Seu áudio tá falhando um pouquinho só.
Yes, I think my connection is late and little. Now it's good. Right.
Yeah, we can hear you. We can hear you.
So then let G the linear group of the 2 plus 2 real matrices and take the control system ut x dot ut xx, where x is a skew symmetric matrix, right? The positive semi-orbit is formed by the matrix of this form with periodic functions, right? And it's easily seen that this is a compact subgroup. Then the positive semi-orbit is a minimal set. Then the identity is uniformly recurrent. We also can find a number tau bigger than 0 and a function u such that var phi tau 1 u is equal to 1. Then the identity is periodic. So I'd like to show you that this situation is a general situation. When the positive semi-orb is a Lie group or a Lie subgroup of G, then all the recursive concept present are equivalent. This is the main result of this topic. So the first result we like to show you is the relation between the dynamical concept of uniformly recurrent point and Lie subgroup. The identity is uniformly recurrent if and only the closure of its positive semi-orbit is a Lie group. It's a Lie subgroup. Actually, it's just a subgroup because this is closed. This is closed, right? Then this is a simple proof. We have a simple proof. Then we have this nice description of the uniformly recurrent point. So, and we also have another nice result that says the identity is recurring even only if the positive limit set is non-negative. So we just take a point G in the limit set of the identity, and we show that this point is recurrent. Then all the points are recurrent, right? This, this is, of course, this is a special property of the invariant control system. Right? Now, we have another description of the recurrent point that just imitate the case of dynamical systems. A point, the identity is recurring if and only if the closure of the positive semi-orb coincides with the limit set. The closure of the positive semi-orb coincides with the closure of all T positive semi-orb, and it is equivalent to the positive semi-orb is contained in the positive limit set. So this is just because of this relation here between the positive semi-orb and the limit set. Right? So, right. Okay. Well, the main reason here relates recurrent set and periodic set. We know that any periodic point is recurring. What about the converse? We know that in the general case, of course, a recurrent point is not periodic, right? In the general case. So, what is the condition? What is the condition in order we have a converse? So we were able to find our answer in this case, in the general case, such that in this special case of invariant control system, the condition that the positive semi-orbit being closed is enough to the equivalence between periodic point and recurrent point. Okay, then if you have if the positive semi-orb is closed, then periodic and recurrent points are equivalent concepts, right? And they are equivalent to the positive semi-orb coincide with the limit set. This is our answer to this problem, to that problem. So a nice consequence is that if the positive semi-orbit is compact, in this case, a compact subgroup, then all points of the invariant control system are periodic. So finally, we'd like to know when all the recursive concepts are equivalent. So in this case, invariant control system, the condition is the positive semi-orbit is a Lie subgroup. So if the positive semi-orbit of the identity is a Lie subgroup, then all the recursive concepts are equivalent. So the identity is uniformly recurrent. If non-Lie, the identity is periodic and the positive semi-orbit is a Lie subgroup. The identity is recurrent and the positive semi-orbit is a Lie subgroup, right? Of course, we need to know, we need to assume that the positive semi-orbit is closed in G, is a closed subset of G, right? So this is one of the main results that we show you in this talk. The details can be found in this paper here, right? And now we are interested in study this concept, this relation for linear control systems only group. I think is a good problem. I think that there are many things to do in this case, and I am excited to study this case. All right. So here we finish my talk. Thank you again, organizing for the invitation.
Let's thank Josiney. So, do we have questions, comments? Anyone?
Hi.
Okay, Rafael.
Professor Josiney, there are some kinds of Lie groups that you will never periodic orbits in the seems simply connected or not. So always the is possible a control system you find a periodic orbit in
Right, Rafael, very good question. We didn't study special case of Lie groups, right? But I know that the existence of periodic points does not depend on the Lie group. Depend on the control system. Depend on the control system, right? And then there is, I know that some cases of invariant control system on new potent Lie groups. Some cases there is no recurrent point, right? Then a good thing, a good condition, of course, is the Lie group being compact, right? If the Lie group is compact, then we have a good thing to find periodic point. But the existence depends on the control system. Okay.
Okay, fine.
Okay. Let us thank again Professor Josiney.
Thank you.